Hello.
Oh, look at Kaiser gets right in there.
Every time.
We're gonna
Dude,
call
I-
Kaiser, I'm gonna call Kaiser the Minute Man, only
Dude,
because he shows up to the show less than 1 minute out.
1 minute, 30 seconds, bro. I think he had a towel on his head when he squeezed in backstage.
I was on time, baby.
Dude, that's impressive.
When you
I don't
say
even
on
know.
time, that's so. If you read my notes when I send them out, it says please jump on 10 minutes early for mic checks. So what are we calling on time here?
Got to read the manual.
That's right.
Oh, he slid
on.
in.
Hang on.
He made it in my yeah.
Let me find. Oh yeah, there's a manual. Yeah, but we didn't need that.
That was the first time I heard him ever say, "Don't read the manual." Unbelievable. But hey, everybody, welcome to the Grapevine. We got Chris Hughes, Eric Kaiser. We got Kevin Hart. We brought him in early, baby.
Yeah, round two.
Welcome
we're-
back.
We're past introductions, man. This is a deep dive episode.
Ooh, let's get into it.
Yeah.
Chris,
So-
you're looking awful spiffy tonight, I must say, man.
So-
you're like,
I got a haircut today. Somebody else styled this dude today. I was like, they were like, "What do you want?" I was like, "I'd like the bald spot to somewhat disappear if you can make that happen."
Is that a comb over?
Yeah, I combed to the side. You know what I'm saying? I don't know. They did good. It cost me a lot of money. I'm like 15 minutes from Eric's house. I'm in downtown Indianapolis right now.
Indianapolis.
guy comes into town, doesn't even tell me he's coming, like last minute.
Yep. So I'm down here. So I'll throw some fun. Like I'm at the ASHRAE summer conference, and I'm sitting in some committee meetings, and I like to just pick up random weird facts from really intelligent people when they're talking. So someone made, and this is probably loose statistics, but I'm sure he's in the background of he should know how many buildings exist in America because of his role in life. But he made the comment that there's like 5 million commercial buildings in the United States. And
Did he count each one?
I don't know how he knew that, but he was very solid in his commenting. And I was like, that's an interesting statistic. Then he said there's 1% of new commercial buildings a year. I was like, wow. So that being said, it's like there's this huge push to retrofit buildings rather than build new buildings the right way. So just food for thought, something to think about, why retrofits are so talked about. Maybe it's because we just don't build as much as we think we do, you know? Anyway,
Yeah.
fun fact I picked up today.
I heard there was a lot of new money coming in for fixing up the old buildings,
Now,
right?
well, that's also commercially speaking. I don't know about, same
Yeah.
probably isn't exactly true for residential.
Mhm.
But-
Actually, I think it might be
Similar?
close. So I read there's around 100 million homes, residential homes, and there's about 1 million new homes a year that get built. So that's about the same ratio.
Yeah.
I mean, at a certain point, like it becomes not feasible to like really tear down the old stuff or abandon the old stuff and just build new, right? Because we've got a limited amount of land.
Yeah.
We've got a limited amount of infrastructure to support those buildings.
Well, also as
And-
material costs rise,
Yeah.
right,
Well,
it may,
yeah.
right, may make more sense to.
I mean, I'm a huge supporter of restoring what's there and keeping the culture alive too. I don't know how y'all feel about it, but I dig an old looking house. You know?
Dude, the Chrysler building? Come on, man. That thing is, let's like keep that up. That's like it's a
No,
monument.
I met a guy this weekend who his job is he gets this like foam sort of extruded or printed, and it's really decorative, and it goes on the outside of the building on the facade, and it's just foam, but then they coat it in a thin layer of concrete, so like it looks like there's this intricate, cool concrete facade, but it's just foam, and that's
Oh,
that's his
yeah.
job, is
Yeah.
is
That'd be
doing that
pretty cool.
decorative stuff.
Yeah, like stucco. Yeah, that's basically.
Yeah, I think there's a name for it. I want to say I even have some of that on the front of my house. It's it's a foam, and then they cover it with like a thin layer of like it's not concrete. The one you're talking about might be concrete or something
It's like
similar, but this is like a
aerated concrete.
stucco. You know, yeah.
Yeah, and it gives it a nice look. Yeah, I watched this guy in the middle of the desert somewhere. He made a metal, just a pull connect, and just made a structure, and then he put plastic, and then he foamed it. Then he stuccoed it.
EIFS.
I don't know
Yeah,
what that is.
I think that is what I have. I forgot what the letters stand for though. So
The acronym I know is RPH. It's for rich people homes.
yeah.
Yeah, EIFS,
Well, that ain't my house.
exterior insulation and finish systems.
Ooh,
Interesting.
Cool.
yeah, that's cool. That's
And
cool
it's
stuff.
let's see, looks like you can get synthetic stucco.
Synthetic stucco. It'll
Cool.
give some
Interesting.
strength to that foam.
Oh yeah, there Robin just put that up there. Huh.
Cool.
That is awesome.
Robin, you're faster than Google.
Maybe Robin is an AI generated voice.
I'm all messed up
Dude.
today, Kev.
You
Oh
got
say it.
my gosh.
you got to
Some
stop
fresh
breathing,
air.
man.
Come back to reality, man. That's why you're not thinking straight.
I gotta dump oxygen tanks in here, like the casino.
All right, let's dive. Let's dive, guys. Let's dive.
Boom.
Hey, so Chris, feel free to
Sure.
take this where you want to take this. I know you wanted the deep dive, but I was thinking with John Ellison, the new filter, we could kind of go deep into how filtration works, like way deeper, like deeper than most people usually go. If you wanted to, we could go anywhere.
Yeah.
So, okay, I will start with let's start with so people who don't know. Kevin has the product or the brand name Haven, right? The Induc indoor air quality sensor that can also do actionable items. And Kevin, why don't you give us a rundown of all the things that product can measure, and then let's go from there.
Sure. Yeah. So the product has a laser inside, and basically there's a laser beam, and the particles intersect that beam, and so it scatters light onto a light sensor, and each little flash of light is counted as a particle. And so we're counting the particles in the air, and typically we're not going to count those particles that are larger than 10 microns, but we're going to focus on the particles sort of down to 0.3 microns, and so almost into the submicron range. And so we're looking at PM 2.5, PM 1 to some extent, and we're doing it in the duct. And we want to know, like, what are the conditions of the duct? So we're looking at temperature, humidity, airflow. So there's a hot wire anemometer in there. It's got 4 thermopiles. So we're measuring airflow. I've actually always thought it'd be a good idea to take a reference airflow measurement with something like the TrueFlow grid, because we're taking a single point measurement. We're not doing a duct traversal. We're not doing a total CFM. We're not capturing the air with a flow hood, anything like that. But I think it'd be good to just take what our measurement is and get an absolute reading. Right now, it's sort of a relative reading. And if you type in the duct dimension, you could turn velocity into CFM, and it could be a rough estimate, and it's going to look at the relative. We can see the speeds very clearly. Like there's clearly off, low speed, high speed in a lot of systems. Those are very defined in our data. We don't do a good job of sort of exposing that data to users right now. But I think we are going to come out. We're kind of worried that people would be like, hey, it says 200 CFM and it's really 150. So I think it'd be good in the future to just maybe show it as a relative measurement of airflow, but eventually be able to correct it using something like TrueFlow Grid. So we're looking at that.
Okay, I
And-
want
yeah.
to come back to that, but keep going. I'm gonna try to hold a mental note.
Well, yeah. Last thing is the chemicals. So the total volatile organic compounds. We look at that, and we're starting to expand into more types of sensors that we can pull into our ecosystem. So we're pulling in radon, and by the end of the year, we're going to be pulling in CO2 and other measurements, and potentially some in-room sensor measurements as well.
Cool. So, all right, here's my first question then. Why do you want to know a total volume of air measurement?
Okay, so we need to know the velocity of the particles, because if the velocity doubled, then the particle count would double if you had the same particle concentration. So if we're measuring particles, we need to know what the velocity of air is, or our particle concentration number is going to be completely off. Right? So that was the only reason we wanted to know. We needed to know, because every single air quality sensor on the market that senses particles has a fan or a pump driving air at a constant speed. And the only way that they can tell you the particle concentration is because there's a fixed variable in the fact that the fan or pump is moving at a constant speed. Now,
Okay,
we don't
so you're-
have a fan or a pump. We're relying
Just
on
to-
the blower of the
Just
system.
just to clarify, are we talking about, let's just say, an air quality sensor device that sits in a room on a table, right? Are you saying those little meters, those have a pump in them?
Even the Aranet,
And that-
it's got a little pump in there.
So not for
Wow.
gases, because gases diffuse differently.
Okay.
It's more homogeneous, right? But for particles, you need to move them across the sensor at a constant flow rate.
Right.
Okay,
that one doesn't do
Okay.
PM2.5. That's right.
Exactly.
Okay.
It has
Sorry-
to do
sorry about that.
PM2.5 for that to be relevant. There are gas sensors that don't
Right.
need a fan or a pump, because they'll
Gotcha.
just rely on convection, diffusion, different principles of air distribution. But as soon as you're trying to measure a particle, you better be measuring the airflow or assume the airflow is constant, right? So we decided, yeah.
And why, I mean, I get that. Are you saying that particles are not evenly distributed through the house, right? There could be concentrated in different areas. And so if you don't have flow rate and air mixture, you're going to have a less accurate reading at that point, because you could just be in a
dust particles. Yeah.
Well, yeah, so one is a gas, one's a particle, right? So it's a physical matter, so it's more influenced by gravity.
Yeah.
Larger particles are going to kind of settle down, right? So you're not going to get a accurate representation of what's in the air if you're just waiting for a particle to move through the sensor. Particles don't move like a gas; they don't diffuse like a gas through the air in the sort of homogeneous way. It's not homogeneous. Particles are not homogeneous through the air in the same sense.
Particles don't
Right.
equalize like a gas is going to try to equalize to where it has an equal distribution, unless it's heavier or lighter than the air. You know, it might distribute up if it's lighter or down if it's lower, but it's going to try to distribute evenly, whereas particles don't. And I mean, what you're saying makes perfect sense now, Kevin. I never really thought about it that way, but you've
Either
got to
did
have
I.
that. You've got to have that speed through there. Because of where you're measured, because you can only measure particles like in that one spot where that sensor is.
Yeah.
Mhm.
You have no
Yeah.
way of measuring everywhere else in the room, so you're
Right.
having to essentially calculate how many particles are in the whole room based on that one sensor
Yeah.
Yeah,
location.
Chris,
actually,
Chris,
like,
think about
if-
this: like a haunted house when they open up that door, and then the dust is like all sitting, and then they move. They move something. It's like
Carefully, you might trigger him.
I watch a lot of Scooby Doo. You know.
yeah, man.
Well, I think
So-
if you wanted to build a particle sensor that sensed particles without moving the air, you might want to build it like a rain catcher. Like you probably want to orient it so the particles would maybe like use gravity to its benefit. But then like the particles would have to be stirred up, and then if you like move past the sensor, you might stir up particles in that one hyperlocal space. So I mean, you also think about it another way. You want to increase your signal to noise ratio. Right. So by moving the air through the sensor, you're also increasing the amount of particles that are going through it, right? Because it's moving at a faster pace. You're getting more
Right.
particles through it. So your signal goes up relative to if you don't have any airflow, you'd just be waiting for sort of a probability, like a chance that a particle would flow through it. By driving the air through at a constant flow rate, you can measure it way more accurately than if you're just hoping a particle would flow through your sensor.
So, man, we just unleashed a host of questions I could ask.
What was your original one that you had?
Well, I got to ask this one. And Kevin, if I'm stepping on your toes and you're not allowed to answer because we're giving away proprietary information, just say no. But I would imagine that you'd have to open up a time sequence for that capture and that measurement, right? It couldn't just be like instantaneous. It would have to be I'm just going to throw a wild wag out there, wild ass guess, but like you capture a minute worth of data and then you average that data to give, your best, measured PM 2.5 calculation based on the 1 minute long time average. And then I bet you're even probably analyzing that average of 1 minute data, taking out, some anomalies that you've probably researched and accounted for during that time capture.
Yeah, so particles, because they're not as homogeneous as a gas, they're much more random. Like you could see all of a sudden just like all these particles and then just nothing for a second and then tick. And then so you really need to average it because it's not as homogeneous.
Yeah.
And so like the outdoor air quality index, they use monitors outside, reference instruments that are moving a lot of air. They got big pumps and they're typically taking a 1 hour average, and that's like really accurate.
Yeah,
Right?
yeah.
But it's
'Cause
not, the time domain of it is not maybe relevant because it's going to miss the fact that you cook popcorn for 5 minutes. That's going to come and go, and it's barely going to affect the 1 hour average. So
Right.
there's pros and cons to how you average that. You're going to be more accurate over time, but you might miss smaller events.
And if your cat scratches its back on the filter grill, you might want to change that.
All right. So here's my
You
next
wanna
question.
change your cat or change the filter grill?
I'd say throw the cat out the house.
Well, I'm allergic to cats. I get rid of the cat.
I'm
but that's
I'm
just
there
me.
too, man.
So when you install a Haven, you have to rotate it, right? It's been a while, but like you rotate it because it's looking for something. What is that all about?
Yeah, so it's looking for airflow. So like if you, for example, have a Haven induct monitor like this one here, and the air's got to flow through the apertures because that's where the laser is allowing the air to pass through so it can measure those particles. But if the airstream is this way and you've got the product and it's blocking the flow of air, the particles aren't going to flow through the product. So I mean this is just a mechanism so that you can find the correct angle of flow.
That's nice. I got the old one.
Oh yeah, this is the new one. This is
Let me
nice.
see the dial. Oh,
Yeah.
that's cool. Okay, cool.
And so it's good because not all systems have a very predictable flow direction. Like if you're in a plenum, like an octopus plenum, so it's maybe like duckboard with flux coming in from 8 different directions, you don't really know exactly what angle the flow is happening through the sensor, right? So this allows you to kind of find the flow. It's like a flow finder in a sense.
It kind of basically what, if I remember from setting mine up, it was you rotate it until you find the highest velocity on the sensor, correct?
Correct. Yeah.
Yeah.
Exactly.
So you're looking for the highest velocity of air based on the internal sensors, that internal anemometer, that internal hot wire, highest velocity going through those 2 holes in there.
Yeah. Yeah. And so we're averaging flow because flow can be turbulent. And then we're also sort of got a average on the particle readings because that's also variable. So you got a lot of smoothing that has to go on to show what looks like a normal particle reading. But if you were to look at the actual like raw particle count at like a less than 1 second frequency, it's going to look totally random until you start smoothing it out, and then you can actually start seeing the nice trends.
I mean, a lot of data actually is that way, and that's one of the things that the electronics can do for us. And it really depends on how these electronics are set up to smooth things out. Because as you said, it can show things and it can hide things depending on what we want to actually see.
Yeah. And I don't know how useful this is, but like because we're one of the few companies that builds our own particle counters, we actually built the algorithm that counts the particles. And sometimes you're seeing this raw analog signal of the light scattering where it's not like you see a particle and then maybe you see nothing and then you see another particle. There's like double hump particles. They're not every particle is a perfect sphere, right? So you may see like the light increases in amplitude and then decreases and then increases and then it ends. And so the question is like, is that 2 particles or is that 1 particle that's not perfectly spherical, right? So there's all these sort of algorithmic counting decisions that you have to make to be accurate. And we've had to refine that over time. And those are things like people don't appreciate, those little like optimizations that you have to make as a manufacturer.
And you could like barely put that into marketing, but I mean that's somebody's really wants to get the particle count right. Which is important.
And the thing is, like, it's really we can't see that, so like we don't see that with our naked eyes. So just to your point, Kevin, like it's really challenging for a user to appreciate everything that goes into that until you actually sit down and really start talking about it like we are here.
Hey,
Yeah.
What one reason I love this show, man, I just love this show is this kind of chat. The reason I say that, I have been humbled to the max since I went to work at TEC. To see like those type of decisions that you just described that I get to witness and like now play a part of, man, that's mind blowing. I wish every technician in the world could experience just for one visit any manufacturer who's deliberating over a decision that's on like a micro level.
Yeah.
And going like, damn, they really have to think about it on that level. And it's like, yeah, they do.
Well, if the company really cares, but the customer doesn't care, then like you're having these meetings internally where you're like fiercely debating the merits of like, should you invest the engineering resources into perfecting something that no one's ever going to notice? But it's like, you have integrity and you care and you want it to be accurate.
That's cool.
You know, so it's funny. Like
you guys probably toss it up a lot. Should we make our own? Would you have the own sensors you guys make?
We make our own particle sensor. Yeah,
that's awesome. That's
but
cool,
from
man.
From another aspect, like I think a lot of customers do care if they knew to care.
Yeah,
right.
But if they don't understand the back end of what that can change, what that decision is changing for them on the front end, like they might not care about it. But if they had the full story and they said, okay, this is what you can do versus this is what happens if we don't do this. Yeah. A lot of them may care depending on what the decision is. So
it's frustrating though, when marketing all sort of washes out, right? So then you have to educate people on something they didn't know they cared about to get them to care, you know, and so now you're spending most of your time, like, instead of actually tackling the emotional thing you were trying to solve initially, you're now like educating people on these highly technical like nuances about why what you're doing is better than what somebody else is doing, because you spent 5 years investing in things that people have no idea.
Welcome to Home Performance.
It's true, man.
That's it,
it's
dude.
true.
Just education. It's like, holy smokes, we just, do a whole show to homeowners. That's what we thought about like one day. Like a lot of education. I just found myself on the phone for an hour with a customer last week.
You guys were like at AHR and you were walking around on the street and you're just like interviewing random people. I remember that.
Oh
yeah, that was fun.
Man on the street.
That was
Man on the street.
That was New Orleans Street Beats, man, during ACCA.
Right. Oh yeah, right. That was it.
Yeah, that was fun. But let me tell you, that doesn't work unless you have the gifted and talented Don Gillis with you. Because Don Gillis has this like showstopper voice.
I know, right?
He's like just a massive
like
teddy
Primus.
bear, right? Like, and people just like, when he speaks, people are just like, I'll do whatever you want me to do. And that's exactly how it happened, because we tried it when he wasn't with us and it was not the same.
Oh my God. I'm going to try some Man on the Streets in a couple of weeks here.
Yeah, we were so when we first kicked off this show and we were putting like crazy amounts of effort into it, like weekly prep time. I don't know if you caught the earliest shows. Like
Eric was doing the news. He was
we had the news skit, and I was trying to get Mike to do Street Beats.
Yeah,
I even sent him my microphone, get up the whole nine. Mike, we need some Street Beats, bro.
But we're bringing it back. I'm gonna go talk to homeowners.
Well, so there's one more thing while we're on this train of thought about particles and counting particles. There's particle count and then particle concentration. And this is like, maybe it's something that people haven't thought about.
Really?
But you can count the amount of particles, like the quantity of particles. But traditionally, so what happened decades ago is that the way that they would measure particles is they would capture them on a little gravimetric sampling medium. So they would pump it through and they'd capture them and then they'd weigh it. So they'd weigh it on a scale like that, because they didn't have the technology to do like sizing and optical stuff that we have today. So they would weigh it and then they say, oh, there's a mass concentration, like the concentration of mass of these particles over this duration of time is X, right? And that became the national standard, was gravimetric sampling, and it was the weight of the particles. But then later what we found out is the weight of the particles doesn't matter. Like, it's actually the size of the particles and the quantity of particles that matter. because those are what are
Oh,
going to get past
that
your
affect
cilia
our
into your
lungs.
lungs,
Okay.
through the alveoli, into your bloodstream, into your organs, through the blood-brain barrier, through the placenta, into the
Wow.
fetus, like all over, right? So that's what's going to do the damage. So we know from a health perspective, and Europe has now started switching to particle count, but America is still stuck on particle concentration, which is the mass and it's the weight. And what we know is that two particles of the same size, one could be lighter, one could be heavier, um, and a larger particle is going to be heavier. But we know a larger particle can't get into your bloodstream, it can't get into your organs, it can't do damage.
Right.
You're fundamentally weighing things and saying they're heavy and saying that a heavier mass is bad. And that's not true. It's like completely non-true. It's actually like a lot of smaller particles with less mass are more dangerous. And so we've really
Right.
got things backwards in
Hmm.
America right now.
Wow. That's wild.
And how do we fix that, Kevin? Like, what's the,
And you know what? He's not even talking about. He's talking from Canada about America here. What's going on, Kevin?
No, okay, North America. We've got it wrong too. Canada has it wrong too. But we just follow what you guys do. So I'm still going to blame you. But like that's
Right.
that's why I was talking about the difference between counting a double hump particle versus two particles. Like that's actually important because two small particles versus one large particle with a big mass. Like we're talking about a fundamental impact of what's dangerous for humans versus what the EPA cares about.
Yeah.
Yeah.
Yeah. You heard it here. All right. We,
I mean,
we
but then
care
you
about
get
the double hump.
like you get into the distance that you're measuring in, right? And you could have multiple particles. Like say you have a big particle moving here and a little particle over here. You could miss that little particle because it's behind the big particle, right?
Yep.
Am I thinking about that right?
Yeah, you're thinking about it right. And actually, there's a concept of capturing multiple scattering angles, right?
Mhm.
And there's something called like me
Oh,
scattering.
Wow.
And so there's different angles of scattering.
Like,
and you can
like
have
Mission Impossible when they had the lasers
no,
everywhere.
I'm thinking it's more along the lines of like when a gunshot happens in a neighborhood and the police station has three detections and they triangulate the signal.
Right.
Mhm.
Is that kind of the same idea here?
Yeah,
Yeah,
that, I
or-
mean that those are both relevant ideas. I mean, one thing you can do is you can build more light sensors. You could actually build an aperture of light sensors. So that's one way to do it. Another thing to do would be to have a mirror, a curved mirror that
Oh,
actually takes the scattering of light from different angles and then points it back down onto your light sensor, right? So that you can think about all the different sort of optical and mechanical
Right.
and different properties where you could even have multiple lasers.
That's
There's
cool.
something called a vertical cavity light emitting diode. There's a VCSEL, and so there's different ways to have. Also, one of the problems with laser light beams is that they're not all Gaussian, and a Gaussian beam is one that has like a very, if you think about like a bell curve, it has like a very nice sort of consistent light amplitude across the beam. So you could have a particle intersect the beam, but at the edge of the beam, and then it appears to be a weaker signal. Whereas if that particle landed in the center of the beam, it's going to be a stronger signal. So ideally,
Oh,
if you're
okay.
sizing particles, you'd want a more Gaussian beam. So the beam would have
Right.
a more consistent bell curve profile. And there's different ways to buy lasers that are more Gaussian, but they tend to be more expensive. And so there's like
Try
a
to-
lot of
Try
trade-offs
to keep the
building it.
cost to something not so expensive.
Yeah.
It's
And
tough.
then you can fire up like the wattage of the laser. So like we use a 5 milliwatt laser, and once you get to 10 milliwatts, you actually now have different standards for like eye safety. So you actually have to have like different certifications because you have a blink reflex at 5 milliwatts that will protect your eye, but at 10 milliwatts, you can actually do damage to the eye without that blink reflex kicking in, and so you're held to a different standard. The interlocking has to be different. It can't be possible for somebody to put like one of those little dentist mirrors in the product and shine it in their eye, and so yeah, it's interesting.
That is
But
crazy.
Theoretically, if you could pump up the wattage of that laser, you'd have a higher signal to noise ratio. You'd be able to detect smaller particles. You'd be able to move the particles more quickly across the laser and still be able to detect them more solidly.
I got a question for you. CO2. if I had no mixing in my house, no AC was going on, and everything was pretty still, would the CO2 float high or low in like a regular house? Is it denser? That I don't know. I was trying to bring my monitor. Like, is it going to be higher on the floor? But my house mixes too much. It's
You're
summer,
saying which one's heavier? Is that
Yeah.
what you're asking?
I tried Googling it one time. I couldn't find nothing.
What's carbon and 2 oxygen compared to typical air?
I guess
And
I could
weight.
search it.
What's
I could
the
search
atomic-
it that way.
Yeah, Eric, come on, what's the atomic weight? I know you're Googling it.
He's on,
yeah,
he's
I'm
on it.
looking
I
at
know
that.
it. What's the weight of carbon
To be-
dioxide?
I don't know if it floats up or down, but it does diffuse in all directions.
Oh,
Like,
okay.
Yeah, I
gases
think
tend
it's,
to
I think
diffuse.
it's pretty neutral.
Pretty
if I
neutral.
remember correctly.
So it'll mix real well. Okay.
It does.
There-
It does. And if,
There's your answer.
if you're mixing the air, it's going to diffuse quicker. So you could, like, if you're breathing in your bedroom and you close up the door and you don't have any circulation, it's going to be concentrated in the
Look-
bedroom, but naturally it
Right.
will eventually diffuse
Okay.
outside of that
I just
space.
want to say, Eric, your wife beat you to it. So.
Yeah.
44 and 28. I'm assuming I don't
Oh
know
my
which
God.
one's which, but 44 and 28.
We have a
Oh,
scientist.
28 is nitrogen. Now, man, talk about the time you need Rachel to jump in the show.
Yeah,
So-
I'll swap out. You asked the wrong question. Let's get Rachel in here.
44 is CO2, but 28 is nitrogen. But I'm confused. What does she mean by 28 is nitrogen? Because air is not all nitrogen. It's
Well, right. Air is air.
right. But
Air is a
it's-
mixture of multiple
mixture.
things.
right. So what's the atomic weight of air? Come on, Rachel. Chop, chop.
Well,
All right, sorry.
it gets complicated.
You got
I know.
oxygen, you got nitrogen, you got
Yeah, this is
all
what
my
you're supposed-
carbon dioxide in there.
Air is 76% into. Okay.
Yeah, 70 something percent nitrogen. The rest is oxygen. And
No.
my carbon dioxide. My high concentrations of
So
carbon
it
dioxide.
sounds like CO2 is slightly heavier than air,
So
is what I'm
my-
reading. So, but it's probably close.
it'll
but it's
probably
heavy.
Yeah.
mix
So
really
there's
well.
your answer right there. Air doesn't have an atomic weight because it's not a single component.
Oh,
Right. It's
Okay.
multiple things. Yeah.
Makes
Nitrogen,
sense, yeah.
oxygen. Yeah. But yeah, I mean, it's pretty crazy. So you guys
Yeah.
are going to do CO2 soon or later on?
Yeah, we'll be doing CO2 probably by the end of the year.
Oh, heck
Um,
yeah. That sounds awesome.
We'll probably be introducing something at the symposium in AHR this next year,
Nice.
25.
That's awesome.
Yeah. No, it's been highly requested, and we think we have a good path to it.
And you're going to integrate with radon?
Yeah, we have that already. So we have that.
Yep.
This guy
There
here, I
it
know you got
is.
one of those too.
Nice.
I'm assuming the big request for that, Kevin, is for ventilation strategy, right? Everybody
Yeah.
wants to reduce ventilation if they monitor their CO2.
Yeah,
That's horrible.
I'm always like on the other side of the debate where I don't think CO2 is as valuable as other people think, and I'll debate people on this. But I mean, fundamentally, it's good to have. Like you want more diverse measurements. You want more of the picture of what's happening. So I'm not against having it. I just think that people are sort of more obsessed with it. They give it more.
Oh, you think they're
waiting-
fixated on it?
Yeah, like a lot
Dude,
of people
I've
don't.
always wanted to have somebody on and talk about just about CO2. Like,
Well,
is it as bad as we really think it is? And I don't
Part-
think it is either.
Part of CO2 is that's what a lot of the standards are written for too.
Right.
Yeah. Well,
Right,
part of
so
this is like, what could we measure?
62.2.
What could we measure affordably, reliably, going back in history? And it was CO2. And
Yeah.
commercial building standards needed to point to something for ventilation. It's basically occupancy, right? Like, so,
Yeah.
so that was the easiest way to measure occupancy and ventilate. So that's what we have. But if you actually dive into CO2 and all the research studies and the cog effect studies that happened, and the toxicity, like the actual effects on human health, don't shock me in the same way that like certain chemicals shock me, in terms of like, I probably don't want that in my home. I
Right.
probably don't want to be breathing that. CO2 just doesn't have that when you dig into the research.
Right.
And so I just tend to think we're over-indexed on CO2.
And you're referring to, they have white papers on like cognitive ability about CO2, right?
They do, yeah. They had the
Yeah.
CogFX study. It was UTC, United Technology Company, Carrier, conducted that study with Syracuse University, and they had, I think, 3 versions of it: CogFX1, CogFX2, and they basically took 2 buildings and they had different levels of CO2, and then people were doing cognitive tests. Like
Okay.
some of them were like
What's your
strategy.
telephone number? What's your address?
some of it was like executive function. Some of it was like related to your reaction times. Like there are
Right.
different types of games that people would play in these 2 different CO2 levels, and they showed some degradation in performance at a higher CO2 level.
What are we at?
And so
Like
that's-
1,500, 2,000?
Yeah, it was like 1,500 versus 1,000 type of thing, and they found some
Yeah,
minor.
I'm not that
variation.
sharp right now.
Well, and one of the challenges too with measuring, any gases is what all do you measure and ventilate for,
Mhm.
right? And then you have to not only look at what's in the building, but what's outside the building and what you're going to bring in to
Right.
ventilate for that.
Yeah.
So there are our standards and our knowledge of all of this and the measurement instruments really need to catch up a lot in order
Yeah.
to really do that well. In
Yeah.
my
Eric is big on, is the accuracy correct?
Yeah,
Well,
well,
I mean,
accuracy is important. And listen,
Yeah.
like we can't, like there's a bunch of sensors we wish we could have that just aren't affordable enough. Like we
Right.
wish we could measure, formaldehyde, and it just is not quite sensitive enough at the right affordability. And like we're almost there. Like I think within the next year or 2 we'll get there. And that's a much better measurement to have than just total volatile organic compounds, because then you're getting like ethanols and things with lower toxicity levels that are kind of mixed in there. So ideally you want both and then subtract one from the other. But CO2, like if you look at it and then you go, okay, it's correlated to virus in the air. Well, maybe it is, maybe it isn't. Like maybe you have HEPA filtration happening in the space, and you could have super high CO2 and 0 COVID-19 particles in the air, right? So like there are correlations. There's occupancy correlations. But fundamentally, like, and even the study, the CogFX study, hasn't been highly repeated by other scientists who have tried to replicate the results, and it was funded by Carrier, who sells ventilation equipment. So that's my little conspiracy theory. But I just it doesn't keep me up at night the same way that like aldehydes would, things
Right.
that are testosterone disrupting, hormone endocrine disrupting, flame retardants, PFAS, like forever chemicals, things that are going
Right.
to accumulate in your body and never leave. Like those are much more concerning, at
Well,
least to
Kevin,
me personally.
I am so happy that you answered that question, because I was going to read those white papers, and you probably saved me about 3 weeks of reading. And
Well,
I
I
was
encourage
I
you
was
to
looking to
still-
get a scientist on from like, I think it was like Austria or something like that, about CO2. So
In general, I think people oversimplify IAQ. Like there's a lot more going on, and the more you dive into it, like ozone's really important. It like accelerates all the chemistry. There's all this chemistry going on, and CO2 is just like one of many, many, many factors happening in the air.
right.
Particles we know are dangerous. They're very straightforward. We know how to capture them. There's like 5 different mechanisms to capture them. You want to layer those together. Like it's very well known that that's going to be helpful. It's going to reduce inflammation in the body. So that's just a really that's probably the simplest thing we have in IAQ. It's just like
Yeah.
take the physical stuff out of the air. We don't want to breathe that in.
Right.
But when it gets to like chemistry, it's a lot more complicated than we think. And I think also the outdoor conditions then, like how do you know that the outdoor condition, we were just talking about this before the show, but like how do you look at the composition of outdoor air and then the composition of indoor air, and then make the right decisions on number
Right.
one, the type of equipment you have in your home, and then number 2, what the right times are to do ventilation. It's actually
'cause
quite
John
complicated.
Ellis was saying that those forest fires, you're not just burning clean wood here. It's not like,
No.
you're burning green. You're burning evergreen. You're burning poison ivy. Who knows you're breathing in, so it's not just woods, and it could be really toxic bringing in that outside air.
Yeah,
So-
it's not just particle. Like there is combustion and there are fine particles, but there's so much more. There's chemicals that are being emitted from all of the wood burning Like there's formaldehyde, for example, in wood naturally. There's different toxins in there that are
Right.
gonna.
Yeah.
There's nitrous oxide. There's all sorts of contaminants that come along with it, not just particles. And so you don't want to bring any of that in. So that's pretty straightforward. But we don't think specifically about like when's the right time of day for the lowest ozone, right? Like where I'd like to see the control
Right.
side of the world going is like actually opportunistically looking at your history of your local weather data and your local indoor air quality stations, and then making the best decisions on when to ventilate based on dew point, based on temperature for
Right.
energy efficiency, but also to avoid mold and contaminants from that side of the world, but also like ozone and particles and and it's much more complicated than
Last episode, you said bringing fresh air in at night was better than than during the day.
it could be for ozone. Like if you actually, you can go right now. Like I
I
encourage
think that's
people to
what
go
you
right
said,
now.
yeah.
Go to like the IQAir website or go to type in EPA AQI and actually like pull up your closest weather station, right? And look at the historic graph of your AQI, and then you'll see that there's all these key criteria contaminants, ozone being one of them, PM 2.5 being another one of them. But there's like I think 8 or 9 criteria contaminants there, and click on them and see like if there's a trend, if there's like a diurnal, like a day and night trend, and then try to imagine like that you had a control strategy that would optimize for those trends for
Right.
your local weather station. Like that, I think that's more
So
important.
I
Eric,
mean,
Eric, hold on there. Can I see the rest of that shirt, please? Can you move over? Is that Bert?
that's my Bert shirt.
What does
baby.
it say, bro? What does it say on there? Yeah, this is my Bert shirt. Shout out to Bert. Mr.
Didn't you get
Tester.
one at the symposium? They had them for
No,
sale.
I
All
ran
you do
out
is
of
walk
cash.
over there and throw a credit card, and they give you a shirt.
I was hanging out with Bert instead of getting a shirt.
I hung out with Bert, and I got a shirt. Everybody should have a Bert shirt.
Wait, hold on. It's a 2-for-1 deal.
That's
Not a
right.
Super Tech.
All right, Kevin, I got
well,
a question.
I'm sorry to cut it. I cut Eric off though.
I got a question here for you, Kevin. Like there's been a lot of talk about ozone here recently, and rightfully so. I mean, it's not a great chemical to breathe in and all this stuff. Can we filter ozone? Can we take that out? Can we break it down back into oxygen?
Yeah, so you can
Um,
actually you can actually absorb it through carbon, activated
Okay,
carbon.
so carbon's the way to do that then.
It's one of the
That's
best ways
cool.
to do it. The problem is everybody, they buy these filters with like the thinnest layer of activated carbon that you can possibly imagine, right? It's basically like a Filtrete, like 1-inch filter, and it's got activated carbon on it. And they're like, oh, great. Like now I don't have to think about chemicals or ventilation. No, like the way activated carbon works is you need physical mass.
You need pounds
like
of
literally go weigh your filter. Like if your filter doesn't weigh 70 pounds, you're not actually like doing a
Oh
whole
my
lot.
god, I was gonna weigh my filter when I did it. I was gonna do it.
There's these huge like drums that are full of activated charcoal and carbon and
Wow.
and the air moves through this. Actually, John Esquivel, when I was on his job site in Austin, Texas, he installed one
John's
of these in a
awesome.
closet. He like literally the whole closet was just this big
Are you serious?
drum of activated carbon, and he had a dedicated duct, and he was just moving air. All the air was moving, like he was pulling air. I think it
and
was
he
out of the
didn't
return
put that
duct.
on the TikTok that he loves.
Dude, I don't know why he doesn't turn his like Facebook
What?
stories into YouTube
Right?
videos, because some of his content is
Dude,
actually
it's
incredible,
insane, right?
and he's super underrated. But some of the stuff he's doing is fascinating. And but he actually had like 50 or 70 pounds of activated carbon because
What?
it was a brand new home, and they wanted to get rid of all the off-gassing chemicals from all the materials in
Holy
the home.
smokes.
And like I'm like, that's a cool, like the fact that the homeowner was willing to sacrifice a closet for that is
That's
pretty cool.
He's been hanging out with John Ellis a lot, so you never know what he's gonna pull out.
But then
John.
people pull out their 1-inch Filtrete with activated carbon. And no, it's you still need to ventilate. You have
Yeah.
not solved the problem.
Yeah, like there's not enough carbon in that Filtrete. The only amount of carbon on that Filtrete filter is just enough to turn it black, and that's it.
Right?
Because it's a
Yeah.
black, it's a black looking filter media in there. But
Yeah.
it's a that I'm sad to say is a marketing gimmick in my opinion.
Yeah,
It is.
I agree.
Because I asked the group, I was like, can I can it convert carbon dioxide? I think even Steven Rogers said, he's like, yeah, if you live on a spaceship, you know, in the shuttle. I was like, come on, man. There's no cheap way. I guess they would fix the CO2 problem for the world by now. But, you know.
I mean, you don't want to ventilate the shuttle. If you start ventilating your space shuttle in outer space, you're going to be in trouble.
It's a good jet. That's how
you will 100% get rid of all the CO2 in the space.
100%. That's a good, ventilation technique right there.
Yeah,
but yeah.
Crank
Chris,
that window down.
Chris has a question.
How do you handle keeping products calibrated for taking measurements like, I don't know, like PM 2.5, for example? How does the calibration work for something like that long term?
Yeah, well, most of the drift that happens in IAQ sensors is because it's something like a metal oxide sensor, where fundamentally there's like a substrate, and that substrate can get contaminated. It can get poisoned, like silicon poisoning. There's different types of there's basically a hot plate, and the hot plate gets really hot, gets like 500 degrees, but it has like no mass, so it's very easy and doesn't require a lot of power to get to that temperature. But there's interactions with that substrate at that temperature that you can measure, but those degrade over time, and so it gets less sensitive over time. And so that's why we really feel like in the IQ industry, these cheap sensors have a lot of drift, because we're using these sort of cheap metal oxide sensors. But with optical sensing, we do laser light scattering. There are ways to maintain a consistent power output for 10 years on an optical sensor, right? You can tune a 5 milliwatt laser. We actually detune it to like 4 milliwatts. And then we've got a bit of a buffer that over time we can maintain that consistently. And one of the main things is like the diode that's emitting light, you don't want to overheat it, because that will degrade the diode.
Yeah.
And so you want to keep it at a good temperature. So like our diode shuts off if our temperature sensor gets above like 50 degrees, because that will start harming the diode. So
like
we
running a motor at low static.
Wow.
You know, you're just trying to let it hum.
It's nice.
Right.
Your product is in a nice cool airstream. That's awesome.
Exactly. And yeah, so we
hot pull down.
We want to shut that laser off, and we pulse it a little bit so that it has a chance to cool down. There's pulse width modulation, PWM, so we do a little bit of that. And so we just want to keep the laser cool. And if you don't use the laser as much, like you could change the duty cycle or the pulse width modulation of the laser so that it's not on as much, and then you can make sure the temperature is lower. And also, you like an engine, you don't want to operate it at like 100% of the RPMs. You want to like pull it down to like 80% of the RPM so that it's not degrading. So you can do a bunch of calculations. There's something called the Monte Carlo analysis, and you can look at like, how do we get 10 years of life out of this laser diode?
Right. And
you can actually calculate that and build that into your product, and then know that you're not going to have degradation. And that's how you get 10 years of life out of a PM 2.5 sensor. But you can't do that with a metal oxide sensor.
So if you're on the fence about picking an air quality sensor, oh, look at this. Look at
Wow.
guest appearance.
Steve.
My man.
Mr. Rogers.
What's up, Steve?
The one, the only.
Chris is turning on speakers, I'll bet you.
There you go.
Yeah.
Hey, Steve.
We're gonna do some hobo.
We got some work. We got work to do, fellas. Work to do.
Is it?
Yeah.
What secret tool does he have that we're not allowed to see? Let me see what that is.
Hey, I got
got the
a
tech logo.
question for you. Have any of you guys, like, you've got the little Aeronet, right?
Yeah.
How many of you guys are using the app for that?
Yeah, I will occasionally
yeah. I
open
got
it
the app.
so that it
Oh,
logs
look.
the data.
Yeah,
Yeah, I got the app.
that was a pretty neat thing to see some of the data graphs and things on that.
So some people want us to integrate with this, but we can't because it doesn't have Wi-Fi. So it's not actually
Right.
It can't be part of a control scheme because it's not actually transmitting data anywhere unless you open your phone and connect to it and download the data. So it's good for historic data, but it's not good for real-time control.
This thing is so much more sensitive than the Yoo-Hoo. Oh my goodness, for CO2. Phew. And it's a little off on humidity, but what are you gonna do?
I think you can
mad at 'em.
calibrate it. I
Oh,
think there's
really?
a calibration factor
Is there somewhere in
software.
the
Yeah,
In
in
the
the app, I believe there is.
Oh, nice. Because I like to bring this thing to, like home performance jobs, just like sit it on the counter and see if they've got like a ventilation problem,
Mhm.
It's like my little, you just throw it in the house and just see where, like a baseline, if is there a big problem here?
So Hausch
cool.
asked, Michael Hausch was asking, have we considered a framework style thing where you could just pop in and out new sensors? That's sort of like in hardware world, we call it like a modular design. We have thought about it, but the problem is, let's say this thing lasts for 5 or 10 years. Like, we are seeing Wi-Fi chips. We're seeing there's a new protocol called Matter that's coming out. There's so many improvements happening in the span of 5 to 10 years that there's going to be so many changes to that product in the next 5 or 10 years that you might as well. And it's not a high cost product. We're not talking about $1,000 or even a $10,000 device. We're talking about a product that's like between $200 to $300, right? So fundamentally, unfortunately, it doesn't really make sense to build a modular design. It would increase the cost. It would increase the complexity, and
You're
you're sort of better off.
Just give a reduced rate on just sliding that into the mount. Just say,
Yeah,
hey, here's a discount.
As long as the mounting plate's the same,
Yeah.
you can just slide the new probe in, 24 volts, like it's
Yeah.
up and running again. It's just way simpler. The design, the cost, and by 5 or 10 years, even the fundamental chipset in there is going to be completely different.
Yeah.
Kevin, you've probably read more on this, but who's behind like the standards of say PM 2.5 requirements and stuff like that? Like where if you were not so knowledgeable in the market of indoor air quality, where would you go to read to find the standards, and who's setting the policy, I guess is what I'm saying. Or is this the wild west?
Well, like I don't know exactly what you're talking about there, but if you're talking about like the threshold of what's harmful in terms of like the micrograms or the concentration of particles, it's the EPA. The US EPA has a standard for America, which the Air Quality Index uses. But then you also have like the WHO has a standard of their own, and they actually went down to 5 micrograms as dangerous. America was at 12 and a half micrograms. And now I think America's EPA is revising theirs to match the WHO's. I don't know if they've already done that or if they're in the process of doing that. But
they revised it down, I think, earlier this year, back in like February.
And that was for what? Ozone?
PM 2.5.
PM 2.5.
Oh, PM
yeah.
2.5. Okay.
So like,
are they handling everything, or is it just I would imagine they're also setting the standards for CO2, radon, everything.
so they see that their jurisdiction is outdoors. Like they care about the environment. They don't care about what's in your home. They don't care about what's in the building. And so this is one of the key problems with IAQ is that most of the thresholds, when we came into this industry 10 years ago, most of the standards were all outdoor focused. So there's no jurisdiction focused on the indoors. And so we saw
that's what I was curious to know.
I just went on the Yoo-Hoo's app and it says source is OHS, Occupational Health and Safety. I don't know who that is.
So like what's relevant for what's outdoors?
CO2, and their EPA has one for radon, but that's all, right?
You said OSHA's got some standards, but
I mean, OSHA has some for
safety.
workplace safety,
Right.
employees in workplace safety, but that's different than homes.
So nobody really took leadership on the indoor environment. Like the EPA was like, our
Right.
jurisdiction's just what's outside, and we're mainly regulating like let's say like industrial plants or sawmills, or that's what they care about. How close are you to a roadway? How close are you to an airport? That sort of thing is what they care about. They don't care about what's happening in your home, and then people care about what's happening on a work site.
EPA's starting to do more with indoor air quality now.
Things are changing totally. Things are changing, but like when I came into the industry 10 years ago, literally I went to the EPA's conference in Raleigh, North Carolina, in the Research Triangle, and I met with them and I asked them about indoor air quality, and they're just like, why are you here? Like, this is not the conference for you. Like literally they told me that's not our jurisdiction. And things have slowly changed. Like now we have the US Green Building Council came out with some guidelines, and but it's all kind of loose. Like I'd say there's no like highly credible body that is enforcing anything in terms of IAQ standards. And so you do see people referencing different standards. Somebody might reference WHO, European or American US EPA standards.
Right.
So Steve was asking, does the radon limit come from the EPA as well? Or
Good question. Not 100% sure.
I believe it does. EPA's got a lot of newer stuff on indoor air quality, and they actually have a thing now that's a EPA Indoor Air Plus qualified home.
Yeah. I'm reading
not-
WHO, World Health Organization, set that
Probably
2.7. Yeah.
Set that up, and the EPA just followed suit.
It seems like nobody really wants to get involved totally. They just want to kind of.
Well, and that goes back to what we said earlier. Like,
I'm surprised Ashley.
there's a certain amount that they can get involved because the knowledge isn't there and the sensors aren't there, and like, what do we do with it?
Right.
I'm surprised ASHRAE hasn't set up a committee for this, to be honest with you. Seems like this should be a standard.
Yeah.
You know?
Wow.
There is. I think they had a bit of a maybe identity crisis around COVID of like, are they more about energy efficiency, or are they more about human health? Like, I think there was a bit of a maybe identity crisis there, and I think they've maybe moved a little more on the human health side. Like minimum ventilation standard is defined in terms of human health, and I think they changed the definition of that. But I could see them moving in the direction of having some standards, and that would be helpful. I think it'd be helpful for the industry to have better standards on what limits to choose. But I mean, fundamentally, you can get the particle level a lot lower inside of a home than you can outdoors. You can't really control what's happening outdoors, but you can control what's happening in your home. And so I do think the levels should be different. You can't just copy and paste the air quality index for inside of homes. And that's one thing we've been seeing is like, if you just shut your controls off at 12 micrograms, you could have just kept that filter running down to 5. Like, why did you stop at 12? If you just copy paste the standards, you're kind of doing yourself a disservice. And I think there's even like, okay, let's step away from standards and regulations. Why don't we just know like what is the best the home can do, like without having to run continuously? But like there should be a slider for homeowners to say like, how much do you care about health versus energy, right? And then if they slide all the way to health, it's going to use more energy, but it's going to get those levels lower. And then we should be able to look at the history of a home and know like, oh, it can achieve like 2 micrograms. So like we know that's achievable. And so that's going to be the standard in this home.
I like that. Yeah. Yeah. Let's
Yeah,
go
I mean,
for the healthiest possible. Yeah, absolutely.
And Rachel makes a good point there too. As soon as you get into the human health, you need to work with the NIH as well. From a standards development.
I'm not letting that-
What is
they're not
it?
coming to my house?
National Institute of Health or Institutes of Health.
Yeah, I think one of the things maybe people aren't thinking about here is like there's no safe level, like nothing is good. You don't like drop below a certain level and it's like, well, this is perfectly fine. It's just like any levels aren't good, and we're just saying like, well, just below this level we don't care. It's kind of, I'd say it's a little bit arbitrary, like somebody's setting a standard, but what's it based on? Because they're changing their minds every couple of years and they're getting stricter over time.
Yeah.
And so like it's not a good thing.
Like
And some of this too, I mean, I look at and I'm like, okay, let's try to minimize it or minimize excess. We need to define what excess is, because we've lived with a lot of this stuff for quite a long time and had some pretty decent lifespans out of humans and some decent health for the majority of people. There's definitely some issues, but we got to figure out is the juice worth the squeeze too sometimes.
Well, I think that's it. Right? It is like, I mean, this is how we're doing it for other areas of heating and cooling. It's like, let's take a sample size of like 10,000 homes in different climate zones, different types of homes, different construction dates, different decades of construction, different building materials. And let's just see like what's normal. Like let's actually build like a bell curve of what's normal, what's possible with minimal upgrades, and what are we capable of without consuming tons of energy. Like what? Let's try to find like the Pareto's law of like what's the 80% we can, what's the 20% we can do to get 80% of the result, and let's like, we need to build a standard from scratch using first principles, not just like pull arbitrary standards out.
Well said.
Forever.
Yeah, absolutely, man. Absolutely.
On that note, we got to go do some work.
Thanks, guys, for showing up. Kevin, I appreciate you coming out again, man. Thank you.
Thanks for having me.
All right, guys. See ya.
See you guys.